All right, so we're going to continue with applications of optimization, and we're going to look at example 2. And on slide 10, it says, if a timber forest is allowed to grow for T years, the value of the timber increases in proportion to the square root of T, while maintenance costs are proportional to T. So therefore, the value of a forest after T years is this generic formula. V of T equals A times the square root of T minus BT, where A and B are constants that deal with the particular timber that you're dealing with. All right, so beginning of example 2, there it goes. It says the value of a timber forest after T years is V of T equals 96 times the square root of T minus 6T, and that's for thousands of dollars. And we want to find its value when it's maximized, okay? That word maximized is our hint that we've got to find the critical numbers and then plug it back into that second derivative to figure out if we have a maximum or a minimum. Okay, so I'm going to take the function V of T, and I'm going to change it over to 96 T to the 1/2 minus 6T, and then we're going to take the derivative, which gives us 48 T to the negative 1/2 minus 6, and then set it equal to 0. Okay, when we solve, we're going to add 6 to both sides, giving us 48 T to the negative 1/2 is equal to 6. And then I'm going to divide both sides by 48. Giving me T to the negative 1/2 equal to 1/8. And what we have is that negative exponent actually puts the T in the denominator. So I have 1/T to the 1/2 equals 1/8. So I can just set those denominators equal or invert both sides. I have T to the 1/2 equals 8. Squaring both sides will give us T equal to 64. And there's our critical number. Sorry. All right, so with a single critical number, we're not sure if that is, sorry guys. Sorry. We're not sure if that 64 is a maximum or a minimum. So we're hoping it's a maximum because that's what we need to find, but we're going to prove that it's a maximum. In order to prove that it's a maximum, let's zoom this out just a little bit. We're going to find the second derivative. And if you find the second derivative, we end up with, negative 24 T to the negative 3/2. And then minus 0, because our derivative of 6 is 0. And we can find V double prime of 64 by plugging that in. So negative 24 times 64 to the negative 3/2. And you can work it out by hand or you can plug it in your calculator. It's not a big deal either way. But when you plug this in, it's clearly going to be negative because a negative times a positive is going to give us a negative number. I don't really necessarily have to figure out what that exact number is. I just need to know if it's negative or positive. Since it's negative, we know that this function is maximized at T equal to 64. And if we want to find what that value is, we can plug 64 into the original function, V of 64, which gives us 96 times the square root of 64 minus 6 times 64. And all of that, so V of 64 is going to give us 384. Well, that doesn't say that it's worth $384. Remember, if you go back to the original problem, that function is in thousands of dollars. So, we can state this answer on slide 13, that the value of the forest is maximized after 64 years, and the value, or the maximum value that they're going to get for that forest, is $384,000. And again, you can graph the function and see that as well. We've got that maximum value at t equal to 64. But we can find it fairly quickly with calculus. All right, let's keep going. So many management problems consist of maximizing profit, which will require constructing the profit function before maximizing it. So recall that your profit is equal to your revenue minus your cost. So such problems have three economic ingredients. The first one is recalling that your profit is equal to your revenue minus your cost. The second ingredient that you need is that your revenue is price times quantity. All right, so for example, if a company sells 100 toasters for $25 each, their revenue would be $2,500. Okay, so if you don't have this written down or have it memorized, you might want to jot that down to keep in front of you. The third piece is the economic ingredient reflects the fact that, in general, price and quantity are inversely related. Increasing the price decreases the sales, while decreasing the price will increase the sales. So to put this another way, or flooding the market with a product drives the price down, whereas creating a shortage drives the price up. So if the relationship between the price P and the quantity X that consumers will buy at that price is expressed as the function P of X, which is called the price function. So the price function P of X gives the price P at which consumers will buy exactly X amounts of the product. This price function, or the price function relating price and quantity, may be linear or curved. Okay, so it could be either way, but it will always be a decreasing function. Okay, so let's look at an example. Example 3, and I'm going to zoom this out just a little bit. Come on. There we go. So it cost the American Automobile Company $8,000 to produce each automobile, and fixed cost, rent, and other expenses that do not depend on the amount of production are $20,000 per week. So the company's price function is P of X equal to 22,000 minus 70X, where P is the price at which exactly X cars will be sold. So we need to find three things. How many cars should be produced each week to maximize the profit? For what price should they be sold? And what is the company's maximum profit? Okay, so we need to find a profit function. In order to find a profit function, we need to find revenue and cost. So we're going to find these three things, but the first thing that we need to find is revenue. So if you look at your revenue function, remember that's P times X. Okay, we were given the P function in our problem. So we have 22,000, forgot a 2. 22,000 minus 70X times X, which gives us 22,000X minus 70X squared. Then we need the cost, okay? So your cost function is given in that first sentence. It cost the company $8,000 for each automobile, and then your fixed cost were the $20,000. So the fixed cost, or the $8,000 per automobile, is 8,000X plus your 20,000 There we go. Plus your 20,000 fixed costs. Okay. The way to find these two works basically the same for every problem. You'll be given a price function, multiply by X to find your revenue. Your cost is what it costs per unit plus your fixed cost. Then we can find the profit function, which is what we need. So that profit function is revenue minus cost. So we have 22,000x minus 70x squared minus, I'm going to have to scoot my thing over just a little bit, minus 8,000x plus 20,000. Okay, when we subtract these out and rewrite it, we end up with negative 70x squared plus 14,000 x minus 20,000. All right. Now, in order to maximize a profit, we need to take the derivative. Okay, so I'm going to pause the video. Or I want you to pause the video and take the derivative of this function and find the critical numbers. All right, so you should have gotten the critical number at 100, and we need to determine, or we need to prove that that is a maximum, sorry. So P double prime, if you take that derivative, we get negative 140, which is always negative. So that tells us that we do have a maximum at x equal to 100. All right. So that's part one. How many cars should they produce how many cars should be produced each week to maximize the profit? They need to produce 100 cars. Okay. The selling price, so this is the answer to part A. The selling price is plugging into that P function. So P of 100. If you plug that in, we've got 22,000 minus 70 times 100. And that would give us, so P of 100 gives us 15,000. Right? So if they produce 100 cars each week and price them at $15,000, okay, then they should make a maximum profit, so capital P of 100, they should make a maximum profit of, if you do 70 times 100 squared plus 14,000 times 100 minus 20,000, then our maximum profit would be $680,000 a week. Okay, so couple things. You've got to find your revenue and cost to find your profit function. Take the derivative of the profit function to find your critical number. Then the second derivative will tell you if you have a maximum or minimum. And then you can answer any other additional questions they give you past once you found that critical number. All right, there's going to be one more video. Sorry, guys. Actually, I think, yeah, there we go. Example, or slide 21 has all of this written out in words for example 3. And we'll do the rest of the section on video 3.